So in previous videos, we've discussed how there's competition on one end of the spectrum, lots of firms competing with one another, and then on the other end of the spectrum, there's monopoly, where there's just one firm. Now we're going to go between those two extremes and look at oligopoly. So oligopoly is a market dominated by a small number of firms. It can be just a few. And we're going to be focusing on, for our purposes, a specific case of oligopoly called a duopoly, where there is only two firms. Now, on one hand, there is competition. Right? There's some level of consumer choice, some competition between firms, even if there's only two. So in some ways, oligopoly industry operates just like our competitive model in that intuitive, logical sense. At the same time, collusion is easy. Competition is there, but it's very tenuous. It's relatively easy for companies to conspire together to constrain production. So in theory, it's pretty easy for them to, even though there's multiple firms, to act as one and be functionally a monopoly. So we're going to try to understand this tension as we move through this unit. And there is like a diagram that we could create for oligopoly, but I want to go a different direction, and I want to make this treatment in terms of a branch of economics, which is originally a branch of mathematics called game theory. So we can think of game theory as the study of strategic decision making. It is this vast area of economics, mathematics. It's originally, like I said, mathematics, but the founder of game theory, John Nash, won the Nobel Prize in economics for game theory because game theory spills over into a lot of economics. And he's not the only person that's won Nobel Prize because of their work in game theory. Thomas Schelling, same story, also won a Nobel Prize because of their work in game theory. So it's this huge branch of mathematics, this massive field, and there's a lot of applications to it. We could do a whole course on game theory, multiple courses, but we won't do a whole course. We'll just do a little bit, but you can see that you'll be able to see there's a lot of expansion. We're also going to focus on something called a simultaneous move game, where each participant is making a decision at the same time. The sequential move games, we're not going to go into that. We're going to do simultaneous move. And that's what makes game theory interesting, because in game theory, each player has no control over what the other player does. Right? You control your actions, but you don't control other people's actions. Right? That's basic. But game theory adds this additional dimension. This really integrates this idea that even though you don't control what other people do, what they do influences how well you're off. It's kind of like an externality in that way. For example, you don't control Andy the arsonist, but his actions affect you if he decides to burn down your store. I should note a little bit of terminology. In economics and game theory, a game is not something that is frivolous or fun. It is a formal setup about the interactions and strategies of two different players, or more. It can be more than two, but we'll just do two different players. Well, the player is someone who is making the decision, is someone who has agency, someone who can act, someone who is making a decision. And a payoff is meant to represent a combination of costs and benefits. So it's essentially the person's individual profit, for lack of a better word, that they get through one particular result. It can be negative or positive, of course. If it's negative, then the larger number is, of course, a smaller number. So -6 is smaller than -3. If it's positive, then 6 is bigger than 3. And that's an important thing to keep in mind. Right? But it's just the basic logic of a number line. Like I said, this boils down to which number is bigger. Right? Though game theory is a potentially very complicated branch of mathematics, a complicated branch of economics, there's a lot you can do with it, a lot of ways to throw in complexity. At its core, it relies on some of the simplest, for our purposes, relies on some of the simplest math you can possibly think of. Which number is bigger? Is it 2 or is it 7? If you've identified 7 as the bigger number, then you can do game theory. So I don't want anyone to be intimidated or scared by this idea that they're doing essentially high-level math, because a lot of the complexity we're going to set aside and we're going to boil it down to its essence. And its essence is the part of game theory that everyone knows and gets introduced to, and it's honestly some of the most valuable parts. So let's dive into it. But before we do, we have to go over a little bit of terminology, one more bit of terminology. So in order to master game theory, you have to really internalize this idea of Nash equilibrium. Right? In order to figure out what happens, you effectively find the Nash equilibrium, or Nash equilibria, as there could be more than one. It's named after its founder, John Nash, name I mentioned before, and it simply describes a state where no one will change their strategy, holding the strategy of the other player or players constant. To get an idea what that means, like consider sitting in a classroom. When everyone sits down, that is Nash equilibrium. Your strategy is the seat that you chose. And while you might prefer a different seat, if that seat is taken, then you are not going to change your strategy. You are not going to change seats. The seat that you sit down in is the equilibrium, right? It represents that equilibrium. When everyone is sat down, no one's changing any seats, that's Nash equilibrium. No one is changing their strategy, holding the strategy of the players constant. No one is changing their seat, holding the seat of everyone else constant. It is not, I should emphasize, it is not a situation where maybe someone would like to be somewhere else. That's going to happen all the time, where someone would like to be somewhere else. It's about, can you unilaterally choose to go to a different spot? If you can unilaterally choose to go to a different spot that you would prefer more, then by definition, it is not Nash equilibrium. So if I really want to sit in the back and all the back seats are taken and I sit in the second to last row, that sounds like Nash equilibrium. So while the basic format of Nash equilibrium is pretty straightforward, find the bigger number, find the Nash equilibrium, you're done, right? That's easy enough. That's not what trips people up. What trips people up is the structure. So we're going to make sure that we understand the structure of game theory, because it's a little kooky, but you have to get used to it because it's how every game looks. This is a blank version of virtually every game you can possibly see. I mean, not everyone, because you can have more than, it can look more complicated than this, but at its basic structure, this is the blank version. There is a player 1 on the left and a player 2 on top. That's how it always looks. And then this column is one of player 2's strategies. And this column is another strategy for player 2. This row is a strategy for player 1, and this row is a strategy for player 1. So in this very basic scenario, which is about as basic as you can get, still make it interesting. Player 1 has 2 strategies, and player 2 has 2 strategies. And we can complicate this by adding more strategies for either of them. We can add more players by having, which gets annoying, but we can do that. But again, for simplicity, right, we're just going to go with this very basic classic structure. In each one of these cells represents a combination choice of strategy choice for player 1 and a strategy choice of player 2. And so there will be 2 numbers here, one representing the playoff for player 1, the second representing the playoff for player 2, separated by a comma. So I'm going to make this as clear as I can by color coding it. Of course, in practice, it's not going to be color-coded, but I want to do it this first time to help you get a better idea of how this works. And I'm also going to name my players. I'm going to call them Alfred and Batman. I like it because it's A and B, Alfred and Batman, 1 and 2. Now in this scenario, I'm making the strategies the same, so they have the same choices, but that doesn't have to be the case. I've now indicated, I've recolored Alfred as red, and I have indicated all of Alfred's payoffs in red. The first player is always the first number in each cell. That is their payoff. It's always the first number in each cell. Batman is blue. He is the second number in each cell. The second player is always the second number. So again, player 2 is on top, player 1 is on the left. Now I have no values in these payoffs, so we can't play the game. This is just to remind you which payoffs go to which player, because it can get a little confusing when you have these numbers and you forget. Right? The second number always goes to the player on the top. The first number always goes to the player on the left. What does this mean? Well, what this means is that when Alfred is trying to choose which strategy he's looking to do, he is going to compare A1 and A2, or A3 and A4, because he can choose the row. He cannot choose the column. You will never compare A1 to A3. You will never compare A1 to A3. You compare 1 and 2, you compare 3 and 4, but you'll never compare 1 and 3 or 2 and 4, because Alfred doesn't determine the column. Alfred determines the row. Alfred never determines the column, he determines the row. So you're always going to compare these two numbers and these two numbers. Batman does not determine the row, Batman determines the column. So if he chooses from strategy 1 to strategy 2, he will go from a payoff of B2 to a payoff, from a payoff of B1 to a payoff of B2. He will go from a payoff, or he'll go from a payoff of B3 to a payoff of B4. Depends on what Alfred does. So Batman always compares 1 and 2, or 3 and 4. If you can keep that straight, you're going to do great at game theory. If you think it's easy to keep it straight, don't say that yet. It takes some practice, but we'll get you there. And we're going to do this with an example. So to keep things simple, just to start us off, I'm keeping with this whole red and blue format so that we can better keep things straight. And I want to see if we can solve this game. So in this scenario, suppose the House and the Senate are creating a bill. They're trying to figure out a bill to agree on. The question is it low spending or high spending, low spending or high spending? So if it's a low bill, the Senate really likes that. The House doesn't really like that, right? So if they in other words, if they agree on a low bill, if the House insists on a low spending bill and the Senate insists on a low spending bill, the Senate is really happy, House is okay. If the Senate insists on a high spending bill and the House insists on a high spending bill, then a 1-5 payoff. The Senate is pretty happy, the House is really happy. If the House insists on low spending, the Senate insists on high spending, they disagree, and in this scenario, the Senate likes it a lot more than the House. And then if the Senate insists on low, the House insists on high, and the House is happy and the Senate is pretty neutral. So I want to emphasize as we play this game that the players always are comparing with things they can control. They're not looking at, say, what the other player gets. So for example, the House might only get a payoff of 2. It doesn't like this result, not because 2 is less than 4. It doesn't like this result because it could change its strategy and get 5. Holding the strategy of the Senate constant, it can change its strategy and get 5. Similarly, it also does not like this strategy, not because 2 is greater than 0. It doesn't like this strategy because 2 is greater than 0. It can't go from here to here. The House cannot move from this cell to this cell. It only controls the column. The Senate might want to go from here to here. The Senate would love to go from 1 to 4, but the Senate can't go from 1 to 4. It controls the row. If we're here, the Senate cannot move here. Only the House can move us here, because only the House can go from high to low spending. The Senate changing that strategy will go from here to here. Player 1 controls the row. Player 2 controls the column. Get that straight. All right. So let's play the game. And one way to play this game is to do what we call cell-by-cell inspection, where you look at a cell, pick one at random, and then figure out would anyone want to change their strategy holding the strategy of the player constant. So let's pick this one, 4-2. Would anyone want to change their strategy holding the strategy of the player constant? Yes. Here, the Senate would like to go from high to low, from 4 to 6. Yes, the House doesn't like that, but I don't care. The House doesn't get to choose. The Senate will choose, and we'll go from high to low. So now we're here. So this cannot be Nash equilibrium because someone would want to change their strategy holding the strategy of the other player constant. So we're here. Does anyone want to change their strategy here? Yes. The House would love to change their strategy. They would love to go from low to high because 0 is less than 3. The Senate doesn't like that. It doesn't want to go from 6 to 0, but I don't care. The Senate doesn't control the column. The House controls the column. So this is also not Nash equilibrium. We can actually even mark these off if we want, right? It's not this one. It's not this one. What about this? Would anyone want to change their strategy holding the strategy of the player constant? Yes. The Senate would rather go from 0 to 1. It wants to do this. It doesn't like 0, or rather it likes 1 more. So yes, they will switch from low to high. And they will go here because 1 is greater than 0. This is also not Nash equilibrium. Does anyone want to change the strategy holding the strategy of the player constant? Here? No. The Senate would not like to go up. It would not like to go from high to low because it would go from 1 to 0. That's bad. And the House would not like to go from high to low because it would go from 5 to 2. That's also a downgrade. No one wants to change their strategy holding the strategy of the other player constant. We circle. Is it possible to have no equilibrium at all? It absolutely is. If I had made that 2 a 6, and the House would like to change the strategy, and then the Senate will change it, and then the House will change it back, and then the Senate will change it, and there's no Nash equilibrium. But here there is. In fact, I'm going to actually indicate that is Nash equilibrium, a little NE. Can you have more than one Nash equilibrium? Absolutely you can. If I had made this 0 a 4, then the House would not have wanted to move away from here. This would still be Nash equilibrium, but so would this. So that's one way to find Nash equilibrium, is to just do cell-by-cell inspection. Another way is to find dominant or dominated strategies. A dominant strategy means that the player in question always prefers that strategy. Like, regardless of what the other player does, this strategy always generates the highest payoff. This strategy is always their best option. It is the dominant strategy, is what they always do. A dominated strategy is something that always yields a terrible option. It's always the least preferred option. It's something that will never yield a better result. Sometimes we talk in terms of it is dominated by a dominant strategy, or like if there's a dominant strategy, then this strategy dominates all the other strategies, right? Because it's something the player will always want to do. In this example, the House never chooses low. 0 is less than 3. 2 is less than 5. It will never choose low. Low is a dominated strategy. But note the house, by definition, because we only have two strategies, the house will always choose high. 3 is greater than 0. 5 is greater than 2. It will always do that. High is the house's dominant strategy. So if we were to play that game again, we could immediately note that the house will always do this, and thus we can completely ignore this part. And that makes things a lot easier. Then it's like, well, what would this end at 1? 0 or 1? Well, it's going to want 1. The end. We pick that one. And we're done. So identifying dominant and dominated strategies can help us solve the thing a lot faster. But it's also a useful terminology. Sometimes there's a dominant strategy. Sometimes there's not. Sometimes there's a dominated strategy, but there's no dominant strategy. That there's a terrible option, but the other options are good depending on what the other player does. And this can happen if you have more than one option, right? Obviously, if we only have two, if one's dominated, the other one's dominant. But if we have multiple strategies, it can get complicated. Okay, so here's a more complicated game. We have A, B, D, C strategies and X, Y, Z strategies. Note that I haven't really created any of these games a scenario, a better background to justify these payoffs. But that's going to come later in our next video. I just want to get us the basics down. So this is sort of a hypothetical. I think I've seen this game though in a textbook, and it was like a football scenario, it was a short pass, a long pass, no, a medium pass, a long pass, and then something else. I don't know, blitz. I don't know enough about football to be able to think what these are. But what's important is that we're going to practice doing our game theory in this extreme version. Now, this is very intimidating. We could go cell by cell, and we could figure out which one is Nash equilibrium, which one's not. But it's helpful to remember our dominant and dominated strategies. If we can eliminate something that someone will never do, or someone would always do, we drastically simplify the analysis. So, take a look. Is there anything no one would do? Is there any strategy no one would do? Okay. So take a look. Is there any strategy no one would do? That's right. D is a terrible strategy. It's terrible. Hey, look, blue gets a payoff of 1. That is awful because if it switches to C, it gets a better payoff. Oh, B gets a better payoff too. Well, sometimes it could get 6, but this is still better. Sometimes it will get -5, but this is still better. This is still better. Anything is still better. So we can reasonably say that never happens. Now we have 3 by 3. Well, now that we've eliminated that, the only reason red would choose Y is because of this outcome, right? In this case, this is the only time where like 2 is better than 1 or -1. This is the only time red would ever choose Y, because then we're looking at -1 here, 3, which is less than 4, 1, which is less than 3, -1, which is less than 0. So the only Y is for this thing that will never happen. Thus, Y is now a terrible strategy. Let's cross that one out too. Well, if we've eliminated option Y, that means that option A is also terrible, right? You get 0 or -3. 0 is less than 4 and 6. -3 is less than 3 and 2. It doesn't have to be less than both. Just to be less than 1. It's less than both. A is a terrible strategy now. The only reason A existed was in case red did Y, and red's never going to do Y because red knows that we'll never do D, or that blue will never do D. So we can cross off A. So now we only have 4 options left. This one, this one, this one, and this one. We've drastically simplified the analysis. And it's pretty clear that when you look at it, if we're here, blue would like to change to 6. Well, if we're here, red would like to change, blue would like to change from B to C. Red would like to change from X to Z, right? From going from -4 to 3. Well, that means blue would like to switch back from C to B. And that means red would like to switch back from Z to X. So around and around we go. There is no Nash equilibrium. So that's the basics of game theory, help you get some intuition to some of the terminologies, dominated strategy, payoff, Nash equilibrium, very important ideas. And that's going to lay the groundwork as we then see what this has to do with oligopoly. Thanks.